Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Today our lesson deals with combustion reaction, and it starts on page 108 and it ends on page 113 from the text Chemistry 11 in Focus. The following concepts will be discussed: combustion of hydrocarbons, incomplete combustion of hydrocarbons, complete combustion of hydrocarbons, combustion of acetylene gas in an activity. I will speak a little bit about the catalytic converter. Combustion is one of the most prevalent chemical reactions since it plays an integral part of our daily activities. The energy provided from combustion is used mainly to power industries, aircrafts, motor vehicles, and to heat our homes. While the energy produced from combustion is essential for these and other functions, the other products of this reaction are having devastating effects on our environment and the quality of our lives. The other products of combustion depends on the nature of the fuel being burned. Our lesson today will focus on the combustion of fossil fuels with the objective of 1. Knowing the disadvantages of complete combustion over incomplete combustion, and 2. To bring more awareness of the effects of the other products of combustion on the environment and living organisms. So these three equations that is seen here show you how, depending on what substance is being burnt, that will be the nature of the other products of combustion other than heat. So here, if some amount of sulfur is being burnt, you will end up with sulfur dioxide. Carbon will give you carbon dioxide, and if you burn a hydrocarbon such as methane, you'll end up with carbon dioxide and water. Now, combustion of hydrocarbon. Hydrocarbons belong to a class of compounds extracted from crude petroleum. These compounds contain only the elements hydrogen and carbon. The combustion of fuels, including those from fossils, has serious implications for the environment. The combustion of fossil fuels, as exemplified by the burning of methane above, produces carbon dioxide and water. Carbon dioxide is one of the gases mainly responsible for global warming. Also, fossil fuels have small amounts of impurities in the form of sulfur and nitrogen. As such, when fossil fuels are burnt, carbon dioxide and oxides of sulfur and nitrogen are also produced, along with some hydrogen sulfide and thiols. Since the oxides of non-metals are acidic, they combine with water, rain, snow, hail, etc. to form acid precipitations. The following equations exemplify how acid rain is formed. Here are the oxides that are produced from the burning of fossil fuel: carbon dioxide, nitrogen dioxide, sulfur dioxide. When rain or hail or snow fall and they come in contact with these gases in the atmosphere, invariably they react with them to form these different acids here. Here you have carbonic acid, nitric acid, and sulfuric acid. And of course, when you study effects of acid rain, you can know the devastating consequences of that. Okay? So now we look at incomplete combustion of fuels. Let us suppose you're burning carbon and you give carbon adequate amount of oxygen. According to this equation here, if you use 1 mole of carbon with 1 mole of oxygen, carbon is completely oxidized or burned to carbon dioxide, with the evolution of 393.5 kilojoules per mole of carbon burnt. However, if carbon is given, say, only half the quantity of oxygen there, it will not be completely burnt. Instead, it is burnt to produce carbon monoxide. And you get only 110 kilojoules per mole of carbon being burnt. So right away now you can see that complete combustion is more efficient than incomplete combustion. So two things are happening here. One, you're getting less energy here, but then this gas that is being produced here is called carbon monoxide, and you know about the deadly effect of carbon monoxide. Something to know about carbon monoxide produced is that it can still be burnt. If you collect the carbon monoxide that is produced and you burn it again in oxygen, you will get that amount of energy per mole. So if you look at this burning here, only this amount of energy you're getting when carbon is incompletely burned. So it means if you allow this gas to escape, you are losing now the difference between this amount of energy and that amount of energy in the form of carbon monoxide. That is why now this is a potential fuel, because it can further be burned to produce all this amount of energy. It is very important, therefore, that when you burn a fuel, you should give it adequate amount of oxygen such that it is burned completely with maximum evolution of energy. If not, some amount of carbon monoxide, as in this example here, will escape, and the amount of energy locked up in this molecule here will be lost. So that is one of the advantages of complete combustion over incomplete combustion. This one is showing you incomplete combustion of propane gas. So if you do not give this enough oxygen here, what happens is some of the products here will be at the lowest state of oxidation, so you might produce some carbon monoxide here and even some soot. So this represents incomplete combustion of another hydrocarbon. Okay, so three effects you might have here. One, you're getting less energy because this has not been oxidized fully, and now you're getting some unburned carbon. Not only are you getting less energy, but you're producing somewhat carbon monoxide, and this is a black thing here, is called soot. And soot can have devastating effect on the environment. So here we're writing the soot produced affects air quality. When inhaled, it can cause a series of cardiovascular diseases. Soot can also destroy surfaces of leaf if it precipitates on them, and also reduces their ability to carry out photosynthesis effectively. In large quantities, it may even affect weather patterns. And of course, we all recently realized the effects of wildfires in Canada on our breathing here. So the next thing we'll do here is an activity in which acetylene gas is being burnt using different fuel-air combinations to see in which case acetylene is burnt more efficiently. Acetylene is produced by the reaction between water and calcium carbide here. Here is calcium carbide reacting with water to give you acetylene gas, or what is called ethane, and some calcium hydroxide here. So these are the materials here that we'll use. We'll have to use some calcium carbide here and water to produce our acetylene gas. We'll need 410 milliliter test tubes, calcium carbide, safety goggles here, a test tube rack, a 1 liter beaker, matches and splints. So these are all the materials that you need in this activity here. So basically what you'll do in this activity is this. You label 4 test tubes, test tube number 1, test tube number 2, test tube number 3, test tube number 4. And then we'll use an indelible marker to measure half the volume of this test tube here, and quarter volume here, and 1/8 of this volume here. So if you use the indelible marker and you mark That part of the test tube there is half of its volume, 1/4 of it, and 1/8 of it. Because we're going to fill those volumes here. This one here will have a full test tube of the acetylene gas. This test tube we will fill with half, 1/4, and 1/8. So what we'll do first of all, we'll fill these test tubes with water and place them in the rack. Then, using your protective goggles and gloves, we'll put our thumb over one of the test tubes and invert it into this beaker here that is having water inside. Start with this with a full test tube of water. Then you take pair of tweezers and you grab a piece of the calcium carbide and you put it at the bottom of the beaker here. The moment you put the calcium carbide there, it spontaneously reacts with water to produce bubbles of acetylene gas. So as the acetylene gas rises, it displaces the water downwards. So in the first test tube, we allow all the water to be displaced downwards. So the entire test tube will be full of only acetylene gas. So when we lift this out, it will be full of gas, so we quickly stopper it and put it back in the test tube rack. That's test tube number 1, where we needed a full test tube. Test tube number 2, we needed half of it to be filled with acetylene gas. So what do you think we should do? It's full of water now. Put a thumb over it, invert it into the beaker of water. If you need more calcium carbide, you put it inside there and you allow the same thing to happen. As the gas rises, it displaces the water downwards, and when it reaches the mark that indicates it's half filled, then what do? You take it out of the beaker here, and then what happens, as the rest of the water falls out, air will take its place. So we will have half of it with acetylene gas and half of it with air. Stopper it, put it back inside your test tube rack. This one, you'll do the same thing. Allow the calcium carbide to react with water to produce more acetylene gas. When 1/4 of it is left as demarcated by the line here, okay, the rest of the water, take it out, water falls out, air comes inside, and then stopper it and you put it there. And you do the same thing for this one here, only you want one of it with the gas. So you put it inside, fill it with water, of course, it's full of water. Put your thumb over it, immerse it inside here, upside down, and you let the gas go inside there. It'll be somewhere here when it's 1/8 full. Alright? You take it out, the rest of the water falls out, and 7/8 of air will come inside there. And that is how you carry out this activity. Okay? It's described here. And this here demonstrates how it is done. Now that we have stoppered the gas, the first one, we will take a burning splint, remove the stopper, and you quickly ignite the gas here. One of the observations that was made is that the gas burned with a yellow flame only at the tip of the test tube and extinguished shortly. A small amount of soot was formed at the tip of the test tube. For the second test tube that has half air and half acetylene gas, this is what was observed. The flame quickly moved inwards and it extinguished, and the entire test tube was coated with a black layer of soot. And the third test tube, now that's the one that had 1/4 of gas and 3/4 of air. You can see what happened there. It burnt with an orange flame. The test tube felt a little bit warm, and you can see only a thin layer of soot is formed here. The fourth one that had 1/8 of acetylene gas and 7/8 of air, this is what happened. You get a loud explosion with a blue flame created there with a loud explosion, and this test tube felt very, very warm. So these were the observations that were made when different acetylene-air combination were used, and each test tube separately was ignited with a splint. In which test tube we think there was complete combustion? Most people will tell you it's the last one, because you had a maximum amount of energy produced, no evidence of soot to indicate any type of incomplete combustion. So In the absence of adequate supply of oxygen, this is what you got there. Now you see, use 2 moles of this, react with 5 moles of that to give you that. Now if you use less oxygen here, I mean 3.5 moles, look what happens. You get some amount of energy. Do you think this energy will be same as that? Look, everything was burned to carbon dioxide and water here. But in this case, look, you're getting different carbon monoxide being produced and some carbon also. And we discussed how this is a potential fuel, and we saw how this could be further be burnt to produce 83.5. So this guy can further be burnt in oxygen. If you give you half a mole of oxygen more, they'll give you carbon dioxide here. Look, that amount of energy is still present in that. And of course, you have carbon coming out there that can give you a further 393. So this is incomplete combustion. And this takes place invariably in any fuel that is being burned, depending on how much oxygen you're giving it. So this will be, if you're going to calculate this energy here, with this type of burning, it will be that amount of energy that will be lost. If you use 2 moles of this, with 3.5 moles of that, of oxygen, and you'll get these products here, that will be the amount of energy lost in this case here. So here you can see that complete combustion is more advantageous than incomplete combustion for 2 reasons. One, you'll get a maximum amount of energy to produce, and you're not producing any of these products here that can have destructive consequences on the environment. This guy is a deadly poison. If you are in an enclosed area of your house and you're burning things, you have to be very careful, because the fuel perhaps could not be getting enough oxygen and could be producing this here and this. You know why this is a deadly poison? Because in high concentration, any concentration, when inhaled, it reacts with the hemoglobin molecules in the red cells, and it takes up the position on the hemoglobin molecules, and it sticks there where oxygen is normally accepted by the hemoglobin molecule. And this, you can answer this question here. Answers are in your solution manual. And there's some other questions here. Why you should, if you're having a home, why your furnaces and stuff like that should be regularly checked. Okay? Something is faulty with your furnace. It could cause inadequate burning of your gas that you're using there, natural gas, and could produce carbon monoxide in your house, which is a deadly poison. Ontario Drive Clean. I think a law was slated in 1999 to ensure that the emission that is produced from the exhaust pipe adhere to certain standards to mitigate the effect of atmospheric pollution. And it was called the Ontario Drive Clean Act. And we have all had to do that years ago, but for small vehicles, you don't have to do that anymore. But the law still applies to larger vehicles. What is happening there is that they go to a certified mechanic who does this testing. What they'll do, they take a tailpipe of your vehicle and they pass through computerized system, and that analyzes all the components that is coming out of the exhaust tailpipe. And they give you the reading, and they compare that with the standard set by the government. And if you do not comply to those, then you have to go and rectify the problem with your vehicle. Smaller vehicles don't have to do that, but they still have to maintain certain standards. Okay? And this is how the catalytic converter works. I'm not a mechanic guy. So let us say that these are the gases that are coming from the engine. Before these gases exit the tailpipe, this is a tailpipe here, started between that and the tailpipe is this catalytic converter here that's made up of platinum and palladium. Now, inevitably, these things don't burn too clean, so there could be some amount of carbon monoxide coming out. You don't want that to exit into the air, so you pass it through this converter first. Oxides of nitrogen, unburnt hydrocarbon, and some carbon. What this guy does is a change. It converts all of these into less poisonous gases. For example, most of the NOx, they call it nitrogen oxide, will be converted to gaseous nitrogen. It's harmless. And all of these, like hydrocarbons, will be burned to give you water, and carbon dioxide. So these gas, except for this one here that causes global warming, all of these here are harmless gases, and we can breathe that in nicely in the environment, right? That is how a catalytic converter works. Some things that can perhaps affect the quality of air: faulty catalytic converters, imbalance of fuel to air mixture, too much fuel is being injected, I not give enough air, some leakage in the exhaust system, unclean filters, air filters. You must ensure for the fuel to burn in your engine, it needs a supply of air, and that is passed through a filter or number of filters. So after a number of months or weeks, depending how often you drive your vehicle, these filters get blocked up, and it impedes the passage of the air through these filters, and that could cause the fuel not getting enough oxygen to burn. You could also have dysfunctional spark plugs. Spark plugs are what provides the energy of activation for the gasoline to burn. There's spark in there. So I forgot to tell you that for a fuel to burn, it needs a certain minimum amount of energy called the energy of activation. It could be in the form of a spark that comes in a spark plug, or a splint or something like that. So that is how the catalytic converter works. All right. And there is a little question here for you based on that. This is a government standard set for you to compare your emission from your vehicle. And there are two vehicles there, A and B. You can look at the emission that's coming out there. You can see which one of them passed the test or which one failed the test. Okay, and these are some questions there.